Okay, hello everybody, I'm Madhavan and the title of my talk is Loop Groups and Quantum Gravity. So I'm going to be talking about the role played by loop groups in developing a quantum theory of gravity. So this is not about Wilson loops or spin networks or edges or links or intersecting Wilson loops. This is about plain old loops generated by an ordinary group of loops. So yeah, this is the outline of my talk. The first part deals with an introduction to loop groups. What a loop group. Okay. It's about what a loop group is. Examines their properties, and we undertake some formal constructions on them as well. And next, we motivate why loop groups are being used to develop quantum gravity, what their link with general relativity is, and what the link with quantum theory is. And afterwards we'll be looking at some observations made by attempting a theory of this. So okay, yeah. So first we start from the beginning. Loop group, say LG, is a group of maps from the circle S1 onto a topological group G. So what we do with this loop group is we introduce a new equivalence relation called the cobordism. Those into algebraic topology would have heard of that. So we have a subgroup of this loop group with that equivalence relation. So you should have seen the simplest cobordism, a pair of pans. So this is to describe something known as the Char-Sullivan product that comes up in string topology. And the virtue of that is the composition there, and the operator that comes with it turns the loop homology into a BV Gersten-Haber algebra, and that, as you know, is a Lie superalgebra with a Z2 grading. Next is yeah. So with the help of that composition, we introduce new products. The first one is what I call the vertical composition. We'll get to what that gamma is over there, and alpha and beta are loops. And the next one is a horizontal composition. These things may seem a little ill-defined at first, but we'll see a little later what they actually mean. And another one called the total product. Okay, so what have these loop products got to do with anything? So we define that gamma over there as the path ordered exponential of a quantity I call the holonomy average of the two loops alpha and beta, and the connection there, the phi AB, is written down is defined in a quantization compatible manner. And after that we propose that the curvature of the connection is the integral over the loop space, that is omega g, of the total product that we saw down there. So this seems a little absurd, but
can you explain the
yes?
integral of a loop?
The loop space. Sorry?
What do you mean?
What?
You say here, you write an integral over alpha, which is a loop.
Yes.
Right?
The alpha
the
that
is a two form, because then it's dx. How
yeah.
can you integrate a two form?
No, that is a one form.
Okay.
Alpha cross. I'm integrating over a one form.
Okay, so what one form are you?
The product there is a one form.
What?
The product there is a one form.
Can you show the pointer which there? Yeah, but up there in the top formula.
This is the one.
No. Go back to the first line of your formula.
Okay. Yeah, this.
We have integral of phi ab dxa dxd.
Yeah.
What does that mean?
That this is the connection. Phi AB is the connection, and I'm integrating over that.
But a connection is a one form.
Yeah, a connection is a one form. Oh, it should have been dxa. Okay, I get it. Yeah, I get what you're saying. It should have been phi A dxa. Okay, I'll correct that. Yeah, so, okay, I'm sorry. That should have been phi A dxa. Here we propose, okay, the curvature of the connection is that. So we provide a concise, sketchy proof of what that should be like. So we do that by defining an inner product on the group with the help of this, and that's a pseudo differential operator that this delta And for the loop space, the S is the Sobolev space parameter, and that expansion becomes trivial for real values. So here it takes a value half. So that so this is the symplectic form that is defined in such a manner as the inner product. So from here it is easy to see that the curvature of the one form is okay. This is justified. So now we get to an important part of the talk. That is, we motivate why loop groups are being used, what they have to do with quantum gravity. First, we examine the link with general relativity. So, as you know, loop groups have a manifest Kala structure, and so does the loop space. So, if you impose a Ricci flatness condition on it, it incurs Calabi-Yau properties. And there's this theorem called the Campbell-Maggard embedding theorem that allows you to embed n-dimensional spacetimes in n+1 dimensional Ricci flat manifolds. So you can see that if you move to higher dimensions, Calabi-Yau, inside of that we can embed a spacetime. So that, yeah. And now the link with quantum mechanics. Loop groups can be thought of as groups of operators on Hilbert space. This is a nice book, nice rendition, Presley Segal. And another useful property of loop groups, or rather the Grassmannian, is Pluker embedding. That is a canonical basis. You'll be writing the Grassmannian of the Hilbert space in terms of these Pluker coordinates. Okay, so here we have just put up some definitions which you can get from a textbook, but we'll just be reminding you of them. Rodolfo Gambini and Jorge Pullen have a nice rendition of this. So if you remember the proposition that allowed me to write a curvature in terms of that total product there, scalar curvature. So one should be authorized to define an action like this. So following this we vary that kind of action to obtain the equations of motion here, and we derive what I call the momenta. So that's written like this. We have a calculation for this, expanding in terms of the loop derivatives that I had shown previously. That is this. Okay, now we define another quantity which I call velocity as the following. The Ix is the interior product, and with this we define another quantity which we like to call energy as a total product between these two. If you remember that, I'll just get back there. Yeah, this one. Between the two new quantities, so that's what I call energy as a total product between the momenta and the velocity over the loop space. So an integral over that. And all of these integrals are well defined because one can find a natural measure that's called a Brownian loop measure, but I will not go into those finer details here. It's just to give an idea as to how loop groups can be used for quantum gravity. See the link. So here are some key observations that I will be presenting in this section. Okay, so the first one is higher dimensions. Why? You can see it from the embedding theorem that I talked of previously, the Campbell-Maggard embedding theorem that allows one to embed an n-dimensional spacetime into an n+1 dimensional Ricci flat manifold. So if I have a 5-dimensional Calabi-Yau manifold, I can embed 4-dimensional spacetime. And also due to the definition of this energy function, that would remind you of the total product we saw previously, which was just the structured equation for that is the curvature of the connection. So due to this, we see that if we move to higher dimensions, it is possible to prove by mathematical techniques that the momenta and velocity behave as cobordinate loops in dimension 5 and above, because 5 is I think it's the dimension least for which a technique I used to prove this, it's called the Whitney trick. So that works only in dimension 5 and above. So yeah, you can be assured that holds. So we write down curvature in terms of these momenta and velocity as follows. So that should appear familiar. Yeah, so we get back to this. As I said, the loop space omega g, it has a manifest Kala structure, and this combined with Ricci flatness leads to Calabi-Yau properties, and yeah, written down the scalar curvature again, and the averaged scalar curvature is given by that total product. So this is to define the energy flow on the manifold. That's given by this, the Calabi-Yau energy. Omega is a Kala form there. And with this, there's an energy operator that's associated with the loop group, and that, so you can relate that to this. As in the energy flow, you can relate with the energy operator, and that's the expectation value on the right hand side. Okay, now we discuss quantizability. We have this interesting setup where you can create an action, you can vary it, you can obtain the dynamics, you can get GR. So now what you want to do is quantize it. And as I mentioned earlier, the connection was defined in a quantization compatible manner. And now getting back to the Pluker embedding that I was talking about, what that does is that creates a holomorphic embedding that can be constructed from the loop space onto the projective Hilbert space. So that's the polarization of the Hilbert space. Yeah. So now we may end up with an overcomplete basis as before, but the equivalence relation on this is you don't really have any group identities that would lead to overcompleteness. You've gotten rid of those, but you have cobordism as an equivalence relation. So you want to sidestep that as well. So what you do is okay, fine, thank you. So you introduce cobordism invariance. There are knots. Vladimir Turav has done some nice work on that, constructing knot polynomials that are invariant under cobordisms. So yeah, like I said, it's necessary to make void the effect of the group equivalence relation of the loops, yeah, the cobordism. So I've reached the end of my talk. The main messages I'd like you to carry is that loop groups can be used as a means for quantum gravity, and prospective. I have not really discussed the quantization procedure in depth, but a prospect for that is Berezin-Toeplitz quantization. And what we've done here is we've sidestepped an overcomplete basis. We've not tackled the problem head on, but we've just gotten rid of that. Some ambiguities that can arise in this theory is relating to the fact that the integration measure, we'll have to look into those details a little more, but is the classical loop theory really general relativity? And when I was talking about the cobordism between the momenta, what I call the momenta and the velocity, that's not unique, so that could be cobordant with other loops. So there's a problem that lies there. And that's just a postscript. That's just put up for fun. Yeah, that's it. Thank you. Yes.
Yeah, so this goes over my head mathematically, but let me see if I just understand this setting, the statement you make. You start with a loop group, you build a theory on the loop group of some group, and you claim to extract general relativity.
Yes. Yes.
So what group is it, the loop group?
An arbitrary Lie group.
Arbitrary Lie group.
Yes.
And how does a four-dimensional manifold arise from the loop group of an arbitrary Lie group?
What I didn't say it arised. I said a four-dimensional manifold can be embedded into the loop space.
The loop space is the space of the loop group, the space of mappings.
Yes. Yes.
One into the group.
Yes. So what I'm saying is that if that is, say, a five-dimensional Calabi-Yau manifold, then by this theorem, the Campbell-Margard embedding theorem, one can embed a four-dimensional spacetime into it. I'm not saying that it arises naturally.
Okay, but back up a little bit. The loop group is infinite dimensional.
Yes, the loop group is infinite dimensional, but the loop space is not.
What's the loop space?
I'm sorry, I didn't get your question.
When you say what is the loop space, what's the definition?
Oh, okay, I get. Okay. So yeah, when you deal with traditional loop quantum gravity, you're assuming holonomy equivalence. I think hoop group. I think in that case, you literally mean the same thing when you say loop space and loop group, but you don't hear. And the loop space is the space of maps from the circle onto a manifold, but that need not be infinite dimensional.
But it is. Why?
Only the loop group is infinite dimensional, not the loop space. That can take any dimension it wants.
Okay, we need to discuss.
Okay.